Hi all. So I'm going to teach you about how to make ray diagrams for parabolic mirrors. The main focus will be concave mirrors. A later tutorial will talk about the less important convex mirror. Concave mirrors are the most important of the three mirrors because it's the most versatile, primarily because it's the only type of mirror that will actually make light converge to a point. And that's significant. That gives a rise to a different type of image that you get when you look into more familiar plane mirrors. So I'm going to walk you through some rules that are shortcuts for how to apply the law of reflection. So we're not going to have to break out protractors and rulers. You want to understand these three rules because if you apply them to any situation with a mirror, it can tell you where an image forms, how big the image is, where it is, what's the orientation of the image, is it right side up or is it flipped over, and then whether it's real or virtual, which are terms I think came up in a previous lesson. I'm going to do one example or two examples. You're going to do the rest on your own. Precision actually is very, very important. So have rulers available even now as we're doing it. I'm going to do my best on the smartboard, but I might lose some accuracy because of that. So let's jump right into it. All right, so concave mirror is, again, our focus. And what you do now is going to carry over when we start doing lenses because it's really the same rules, just applied for a slightly different phenomenon. So concave simply means if I draw a curve, if I'm looking here, if my eye is here, then it's caved in. If my eye is here, then that's a convex. So the rules, the law of reflection still holds, but the consequences of that curvature radically change how the images form. So the basic rule of a concave mirror, it takes, if we look at parallel rays of light, and this is a fact you want to know, generally come from distant sources. The sun is a prime example. The sun is so far away that by the time the rays of light reach the earth, they're essentially parallel, even though technically they're spreading out from the sun. So in this class, if we have a source of light that is more than, let's say, 10 or so meters away, the rays coming in are essentially parallel. Anyway, they cause the rays of light to reflect in such a way that so this should say they, not the, that they converge. Okay, so converge is a fancy word for focus. They converge at what we call a focal point, F. So let me try to do that on the diagram here. So we have our 3 or 4 parallel rays. Here is our concave mirror. And what you want to do with your ruler is line things up such that when the rays reflect off the mirror, they go through that point that's called F. So I'm going to try to do that here. So it's going to go out, and you really should put an arrowhead on it because we're indicating the direction that's going. So let me change that for the other ones. And it goes through here, and I extend it out. Technically goes to infinity. I can already see I'm a little bit off, but that's all right. It extends through F, and then this one goes through F. So if you shine sunlight into a parabolic mirror, concave mirror, all that light will come to a focus there, and it'll be an intensely hot spot. This only works, again, if the rays are coming in parallel, which generally means your source is far away. What we have to learn is, what if your source is close to the mirror? How do the rays behave? Okay, they still follow the same rules. It's just that they're not all going to converge in the same spot. Well, excuse me, they are going to converge in a spot, but it's not going to be the focal point. Okay, so let me give you some key vocabulary, reference points on these diagrams. The first one I've already mentioned, the focal point F. It is the point where light from distant source converges. Okay, so the only time rays of light, or any wave I should say, because it's not just light, sound would do this, water waves would do this, the only way that something will ever converge at the focal point is if they're coming far away, or put another way, they're coming in all parallel to each other. So when you go to form images, don't get in your head that the image is going to form at the focal point. That's a very common mistake. Another important reference point is called the center of curvature. So if you think of a parabolic mirror as a part of a circle, even though it isn't, the center of curvature would be like the center of that. And an important mathematical relationship is center of curvature by definition is twice the focal length. Okay, so that's going to come in handy in certain applications. So let me now show you the rules for ray diagrams to help us locate images when an object is closer than infinity, which means that it's somewhere near the focal point or center of curvature. And then I'm going to demonstrate it down here. So have your ruler ready for that so we can get a somewhat accurate image. And then I'll do one more example, and we'll talk about summing up all the possibilities into a nice chart on the third page, I believe. Okay, so you got 3 rules to draw 3 different reflected rays. When you go to do problems to figure out the image, you only need to use 2 of those. 2 are enough, but it's nice to have 3 depending on the situation. Okay, so one we've already talked about indirectly. Any ray parallel to the principal axis. So this line here is the principal axis. Generally, we center a mirror on that. It doesn't have to be, but it's just convenient. Okay, any ray coming in parallel must reflect, I don't know if that says reflect, but it should say reflect, through the focal point. So I'm going to do each one at a time and develop an image. So let's take a look at the situation here. I have an object here, this arrowhead. So the base of the arrow is on the principal axis, and then here is the arrowhead. So I'm going to draw light that comes off that arrowhead, kind of like we did in the previous lesson with the mirrors. So one of the rays that's convenient for me to understand is one that comes in parallel to the principal axis. I've already drawn it. So what I want you to do with your ruler is, like the problem above, is draw a straight line through the focal point and put an arrowhead on it. So that represents one of the reflected rays off the arrowhead. And the important thing is, let's keep in mind, you, the observer, are out here in front of the mirror. You could be here. In other words, you're looking into the mirror and you're trying to see where that arrow appears in the mirror. So the point of that first ray is, what it's telling us is the image of that arrowhead must be somewhere on this reflected ray. So in order to pinpoint it, we need another reflected ray to see where it intersects our first one. So we have 2 other rays that we can draw following the rule. So let's get to the second rule. Any ray that passes through the focal point reflects parallel to the principal axis. It's just the reverse of the first rule. So I'll do my best here, so let me get that. So I'm going to draw a ray starting from the arrowhead. I've already messed up, but I'll fix that. And I pass it through the focal point. And if I do it correctly, so let me just try to, crap, I don't want to do that. Give me a chance to correct this. Again, this is where the precision of the smartboard is really messing me up. Okay, I'm not going to correct it. Anyway, so I'm going to reflect this parallel to the principal axis. So I'm going to eye it up as best I can. It's a little off, but I'll just live with that. I can't, it looks fairly parallel. So there's my reflected ray 2. The point of this is, let me put an arrowhead here, is the image of that arrowhead as seen by the eye when looking in the mirror is at the intersection right there, where those 2 reflected rays intersected. So in other words, what I'm saying is, if we were to trace all rays of light that are hitting the mirror everywhere along here, they would more or less pass through that point there. So that's where the image is. But before we draw an image, I want to give you the third rule. The third rule is probably the simplest. Any ray that passes through the center of curvature reflects straight back. That really just follows from geometry. Anytime you draw a radius from the center, you are hitting the tangent perpendicular, right? Perpendicular at that point. That's a rule of geometry. So the reflected ray, incident ray is 0 degrees, so the reflected ray has to be 0 back. So if I attempt to do that here, okay, then I draw from here a ray through C, and it would come straight back. I'm not even going to try to draw that straight back. I'll just do it in a different color. But notice it passes through that same point again. So I've done a pretty decent job. Okay, so what is the, whoops, I probably didn't want to erase that one, but that's all right. So what's the point is, the arrowhead head is right there. So where is the rest of the arrow? Well, if the rest of the arrow starts on the principal axis, I'm not going to go through all the details, but any light that goes through here is going to come straight back because it's going to hit perpendicular to the flat line there, that tangent, or I should say really it's going to be 0 degrees to the normal. So the body of the arrow, or excuse me, the tail of the arrow is always going to be on the principal axis. So there's one part. So what I do is I go from the principal axis to here and I draw my arrowhead upside down. That tells me that the image is going to be inverted. Okay, so there's a few things I learned from this ray diagram. I'm going to try to draw a slightly better image of that. And that's what you want to put there. So when your eye is looking into the mirror, excuse me, it will see an image here. So we can summarize what is true of that image. Well, actually, I'll talk about that later. So here's what I want you to do right now is let's go to the next page because this is where we're going to practice for various situations. You're going to have to know all these situations or at least be able to draw them, and then we're going to summarize them on this matrix right here or this table. So let me make clear what we have. So all we're doing is we've got a mirror of a particular focal length, and that focal length is dependent on the curvature of the mirror. The more curved it is, the closer the focal length is going to be to the mirror. The less curved it is, the further out it's going to be. In fact, if I have a plane mirror, the focal length is infinitely far away. Anyway, so all I'm doing is I'm starting my object far away, but not infinitely far away. So the reference we say is this is beyond C, okay? It's beyond the center of curvature. Then the next situation is what happens when we place the object at the center of curvature. Then we look at what if we're between the center of curvature and the focal point. And then lastly, if this damn thing would work, then I go inside the focal length. And this is the one that's going to give you the most trouble, but I'll let you try to figure it out. Okay. Actually, you know what? Let's do that one together. Why not? This is one that you see very commonly in tests. So let's do this one. So I've got my object inside the focal length, and I want to understand where the image is. So I'm going to try to follow 2 of the 3 rules that we did on the other side. So I've already started one. I'll actually do the first one. Let's draw a ray parallel to the principal axis. So we're going to draw it in parallel like this. And if you recall from the rules, then that must reflect through the focal point. So line up your rulers and draw a reflected ray through the focal point like that. Okay. The second one I've started for you because this is the one that gives kids most trouble when they're on their own. The second rule says what happens when light passes through the focal point. Well, since we're already inside the focal point, what we have to do is we've got to pretend that light comes from a distant source and passes through like this and then hits the mirror. Okay, so it is passing through the focal point even though it's not coming from the actual light source, but we can imagine that light that follows this trajectory would have passed through the focal point if we go backwards. Anyway, the point of that is if it goes through the focal point, or it seems to come from the focal point, then it's got to go out parallel. I know I haven't done a great job with the parallel there, but you can do a better job than I. Now this is where things get interesting. Your eye is right here. So it sees this ray and it sees this ray, and it would see another ray that passes through the center of curvature like this and goes straight back. Okay, but don't worry about that third one. The point is those 2 rays never converge. Okay, they will never converge out front. So what the eye does is, like a plane mirror, it thinks those rays came from a common point, which would be roughly right there. So that's where the arrowhead appears to your eye, behind the mirror, like a plane mirror. The bottom of the arrow will appear directly below it. So if I draw this in, there is my image. So now I can characterize that image 3 ways. I got to hustle here. And I'm going to go to this chart right here. So we are inside of F, and I want to look at where is location. So it is behind the mirror. Secondly, what's its size? I'm going to put big M. It's magnified. What's its orientation? It is upright. In other words, when you look in the mirror, it will not appear flipped over. And what type of it? It is virtual. Virtual because there's no light coming to a focus at that point. What happened to our... Okay, since no light is actually reaching here, but your eye thinks the light from this arrow is coming from there. So that's why it's virtual. Try the rest with these. Okay, these are a little bit simpler. This one, you got to be really precise. All right, I'll give you a hint. The image should form right at C, even if it doesn't look like it does.